morning, welcome back. So yesterday, remember we discussed basically two topics. The first one was the story of the entanglement entropy, that if you have a gap system, you obey the area law. So if you have a 1D system, basically the entanglement entropy is a constant. And if you have a 2D gap phase, it's just proportional to the perimeter between the two regions A and B. We also discuss if you have a topological phase, the first correction to this term is the topological entanglement entropy, which is a universal term that only depends on the nature of the excitations. So that was one story. The other one was about the entanglement spectrum. The entanglement spectrum is just the spectrum of the reduced density matrix. And we look, for example, at the AKLT spin chain, which is the simplest example that you can build for an n-body interacting system and topological phase. It's an SPT. And when you cut your system into two and you look at the entanglement spectrum mimics the edge physics of your system. For the AKLT, it's just a spin 1/2 at each end, and when you cut, you create a virtual edge, and at this virtual edge, you have this spin 1/2 degree of freedom. So there's and this is quite surprising because you have only two levels in your entanglement spectrum, where you expect an exponential number of levels if you increase the system size. So I also started talking about the matrix product states, and I've shown you how to explicitly build a matrix product state representation for the AKLT model just by using 3 2x2 matrices. Using these 3 matrices, you can rebuild all the coefficients of the AKLT ground state just by taking the product of as many matrices as you have spin 1 and taking one matrix element. And this does not depend on the number of spin 1 you have in your chain. So the question we were left yesterday is, why do we need a 2x2 matrix, not one a 10x10 or 100x100? And the more surprising, why only 2x2, whatever the number of spin 1 we have in the system? So the size of the matrix, which we call the bond dimension, we'd like to show you now that this is actually related to the number of levels that you have in your entanglement spectrum. So let me first rewrite the formula, the generic formula for the MPS. So take your quantum state, so you decompose your state on some many-body basis, like the spin 1 basis, where you have M1, M2, Mn. Pick your product of B matrices. And each time you look at the same matrix element, whatever the coefficient you look at. So you don't change alpha L and alpha R, depending on what you have here. It's always the same matrix element that you pick. So that's the matrix representation of the state psi. And now what we can do actually, let's say we have the system. You can think about the AKLT model. Here for 1, 2, 3, 4, 5, 6, 7 sites. And let's cut it like this. So we will consider for A all the spin 1 from 1 to LA. And now the B part will be made of all the spin from the site LA plus 1 to N. So it's just a way to cut the system into two. Now, if I look at this formula, I can explicitly separate the product of B matrices by looking at the first LA matrices and all the remaining one. So let's make this product explicit. So you got some of all the configuration, some of the alpha, which goes from 1 to the bond dimension. And now you have the product BM1 dot BLA alpha L alpha BLA plus 1 should be BMLA, sorry. Oops. BMN, far right, and I still have MLA, tensor product with MLA plus 1 dot MN. So right now it's just rewriting this formula by making this cut explicit, where I split the product of matrices, where by having LA matrices here and all the remaining one here, and I also split the tensor product into the orbital from orbital 1 to orbital LA and LA plus 1 to N. Okay, so I can now rewrite this as sum of alpha from 1 to the bond dimension, A alpha, tensor product, B alpha, where I will define the A alpha as the sum over M1 to all the configuration for the first LA spins, from BM1 to BMLA and B alpha as the sum over LA plus 1 MN. So here it's alpha L alpha, and here ML A plus 1 B MN alpha R B MLA plus 1 M. Okay, it's just this formula where I can commute the sums here and rewrite as a sum over alpha of something that all belongs to A and tensor product something that belongs to B. Now, if you look back at the definition of the Schmidt decomposition, right? Remember the Schmidt decomposition was something like psi was sum over I minus psi I AI, that's a product BI, and where AI AJ is equal to BI BJ is equal to delta IJ. Right, so that's the definition of the Schmidt decomposition. So when you look at this formula here, it smells like a Schmidt decomposition. It's not exactly a Schmidt decomposition, right? Up to some normalization factor, you're fine, you have only positive weights. But now if you look at the vector A alpha and B alpha, so you have like the same kind of sum here, where you get the same indices for the A and B, but now there is no guarantee that you satisfy the orthogonality condition. So if I take A alpha and A alpha prime, they don't have to be orthogonal. Actually, even A alpha doesn't have to be normalized, is not normalized here. So I need to perform some extra steps to make this a Schmidt decomposition. But even if you stop here, there is one crucial remark that you can make. Whatever the, so this guy here, the alpha, the A beta, they might not be linearly dependent. So it means that actually, when you will do the Schmidt decomposition, going from here to here, you might kill some states in the sum. So the sum here might have less terms than this one. But it's going to have more terms here than here. So just by looking at this, you can see that the relation between the bond dimension and here, the number of terms that you have in this sum is actually the number of levels that you have in your entanglement spectrum. So whatever happened, the bond dimension cannot be lower than the number of levels that you have in your entanglement spectrum. So somehow, what the entanglement spectrum tells you is what is the minimum value for the bond dimension that you have to pick. So that's why it's not surprising that for the AKLT model, we only need a 2x2 matrix to write down an MPS representation of the ground state. It's a 2x2 matrix because if you do the entanglement spectrum of the AKLT ground state, you have 2 levels. That's it. Not 81, not 100, 2. So if you really want the full derivation to go from here to there, the only thing that you have to do is a bit more algebra. I hope I won't screw up this one. So we have psi like this. So you can define, you can extract a basis A alpha tilde, where alpha tilde, A alpha tilde prime is delta alpha. So this is an orthonormal basis. So extract an orthonormal basis from the set A alpha. So this will be your orthonormal basis. And you can rewrite the A alpha as a sum over alpha tilde U alpha tilde A. Right. You have a basis which is not orthogonal, which is not normalized, and might be overcomplete. So from there you do some Gram-Schmidt or whatever to extract a basis of linearly independent states A alpha tilde, and you just rewrite the previous state using this new basis. Okay? You can do the same for the B side. So you define some B tilde, which is going to be the sum of a alpha tilde, such that you can rewrite this as B beta tilde, alpha tilde B alpha. This is the normal complete basis. And using this, you can rewrite psi as sum over alpha tilde beta tilde U dagger V U transpose V alpha tilde E tilde alpha tilde B beta tilde. Right. So just using the relation between the orthonormal basis and the set A alpha and B alpha, I just plug these formula there, and you can rewrite psi like this. And you see this is the entanglement matrix that we have I've described yesterday. So on this entanglement matrix, you can perform an SVD and get the entanglement spectrum out of there. But you see that the index alpha, tilde, and beta tilde, they cannot be greater than the bond dimension, right? In the best case, your basis here is complete. All your states are linearly independent, which might not be the case. So there's some here as a chi tilde, which is lower or equal to chi. So which means that in your SVD you have at most chi tilde non-zero eigenvalues. So this gives you the number of levels. So to summarize here, each time you have some quantum state and you perform an entanglement spectrum, if you see that the number of levels that you have, it's much lower than expected, and especially if it's exponentially lower than what you expect naively, it means that there is an efficient way to rewrite your quantum state using a matrix product state. So these lectures are not about matrix product state, but trust me, you can do lots of calculations in a very efficient way once you have the matrix product state description of your wave function. Good. Any questions? No? Okay. So if not, let's move now to another example. The goal, of course, is not to look at a phase like the AKLT model. I mean, it's a 1D phase. It's an interesting one. But our goal is at some point to look at a strongly correlated system in 2 dimensions. So a first baby step in that direction is actually to look at 2D problem, topological phase 2D problem, but non-interacting ones, such that the integer quantum Hall effect. So I don't remember what was the title of this lecture. Let's see. Was observing an edge mode. Through the entanglement spectrum. And first I will focus on the integer quantum Hall effect. So fortunately for me, Karian has done all the dirty work of introducing the Landau levels, the integer quantum Hall effect. So I will assume that you know that everything by heart, like all the formulas, all that kind of stuff, and I can go faster. Still, what I will focus on now, I will only look at the lowest Landau level, field. So the nu equal 1, spinless. Let's take the simplest example, spinless fermions. So I will use the symmetric gauge. So just to remind you, the one-body wave function will look like this. It's 2 pi 2 to the m factorial. You get a 1 over LB. I think you use L not in your notes, right? For the lemmatic length. Z over L naught to the power M. Where M is a positive integer. And up to some h bar factor, this is just the angular momentum of your state. Okay, so Z is the complex coordinate of the electron, dx plus Iy. M is the angular momentum of your orbital. L naught is the magnetic length. So for simplicity, we will set L0 to 1. So that's the scale in your problem. What else I have to say here? Yeah. So maybe if you plot these orbitals, they look like rings. So this is the m equal to 0. Then you've got the m equal 1. This is the m equal 2, and so on. And the typical radius of each ring goes like the square root of 2m. And the area of each orbital is like 2 pi lb square. I think you have this picture about the what's going on to your Landau levels once you have a confining potential. So if your confining potential, the variation of the confining potential are slow compared to on the scale of the magnetic length, what you will do is just your Landau level will follow the confining potential. So if look what's going on, this sketchy picture. But I put m, so remember that m is like r square to this relation here. So I will get something like this. And so this is my confining potential. And then I have the other Landau level. Let's put it like this is the energy. Get one level here, and this is cyclotron energy, h bar omega c. What I will do now is to fill completely the lowest Landau level in the bulk. So let's do it like this. And I put all my electrons there. And this is the densest state I can create. So this is the Fermi level EF. So the spectrum of the H mode is actually this linearized chiral mode that you have here. Remember, the angular momentum, you go only in one direction. These are chiral mode. So so this is the single particle energy spectrum, right? How do I write the many body energy spectrum out of there? So energy, this m, well, if you prefer, it's the momentum or the angular momentum, it doesn't matter. So you completely fill. So now I look at what's going on at the edge, so I can linearize the edge mode here. I can completely fill up to the Fermi energy. And this is going to be E0. This is the ground state energy. Okay, so I completely fill this. Now, if I want to create an excitation, this in terms the smallest excitation in terms of energy that I can create is basically to promote one particle from here to there to the next level. Right. So this one to promote it here. So let me plot it once again. Now I get an empty orbital, and I put one here. So remember, this is a linear spectrum, so the energy as a function of m will be given by 2v over L times m. There is some h-bar factor missing, but let's not focus worry about that. This is the edge mode velocity. This is the perimeter of your edge. So now I have like tons of empty orbitals. So if I plot what's going on in terms of energy for the many-body problem, so I start with the energy E0 by summing all the states, all the empty state here. So I will plot E minus E0, still the momentum. I have one state at energy E minus E0. When I have the momentum equal to 0, I can always take the reference of momentum to be 0. Then the next, the smallest excitation I can create is to promote this guy here to here. This will create an energy 2 pi V over L compared to E0. And I have a single way to do that. Okay, now the next excitation. I have, in that case, two options. I can promote this guy to the next level. So there we'll get two empty orbitals, and I occupy this one. So this creates, compared to this one, the energy is 2 times 2 pi V over L. This is one option. So I can promote this guy here, or I can promote this guy here, because there is an empty orbital. Okay? Or there. So which will be like this. And now I have this empty orbital here and occupied orbitals all the way down. So these two, they have exactly the same energy. So in your spectrum now you have two levels at energy 2 pi V over L times 2. And you can go on like this. So once again, in the next case, you can do the calculation by yourself. You will get 3 degenerate states. At the next stage, you will get 5, then 7, and then 11. So this is the many-body spectrum for the edge mode. So I can construct the many-body spectrum from the one body just by looking at all the excitation I can, how many ways I have to do one to create excitation at a given energy. So the one thing you should remember this counting, this one, if I put it like this, so this one is a single state, 1, 1, 2, 3, 5, 7, and so on. if you remember your lectures about the integer quantum Hall effect and the edge mode of the integer quantum Hall effect, so Karian has introduced the bulk wave function for the system. It's just a later determinant for all the occupied orbitals. So it's the Zi minus Cj exponential minus sum over I for L. Let's put this. This is the many-body wave function. So if you look, you can also write down the many-body wave function for the edge excitation. So this is the ground state, this guy here. This guy here, there is a single polynomial that you can write down, will just be the sum over I times the nu equal 1. Here you can write down two edge modes. Basically, one will be sum over I Zi Zj. I'm sure we'll mess up this one. So Zi Cj 1. So you can create two linearly independent polynomials and the Zi square. You can also, this one is just the square of this one, and you have to include this one, and so on. So in the same, I mean, you can, for each state here, you can write down the many-body wave function for not only the edge, but the edge plus the bulk. Okay, it's just the nu equal 1 state times some polynomials, and for each degree, you can. There are these numbers just give you the number of linearly independent polynomials that you can write down. So the goal that of what I will talk about today is when we do the entanglement spectrum for this guy here, which is the ground state of my system, I want to observe the edge mode. So I want to get an entanglement spectrum that looks like this. Maybe just in terms of notation, because I will need it. Sometimes it's quite convenient to use boxes, and it's 0 and 1 to represent a state. So for the nu equal 1 state, I can write it like this, where I have one box for each orbital. So this is Lz, which means M. One, two, three, 4, 5, 6, 7, 8. And if I represent the occupation like this, the nu equal 1 is just I put one electron in each box. Right, or if you prefer in second context notation, it will just be sum of n factorial, the product from m equals 0 to n minus 1, C dagger m acting on the vacuum, right? So this is an occupied orbital. And this one is an empty orbital. Right. Okay, so now we have all that we need to do the calculation. So we have described the nu equal 1 physics, or remind you the nu equal 1 physics, or you write down the wave function, or you look at the one-body spectrum, and out of that, you build the many-body spectrum. So what we want to do is we have, let's say, your quantum mole droplet, integer quantum mole. And we want to cut it into two parts, A and B. So first, if you look at the way I've written down the new equal 1 state here in terms of occupied orbital, it looks like a 1D problem. You have, it's like a lattice going from 0 to whatever, the number of flux quanta in your system. And I can say, okay, it's like a 1D lattice, and I cut my system into two in this lattice representation. The thing is, if you do that, if you cut your system like this into A and B, well, here is just a product state. So if it's a product state, the integrated spectrum is trivial. You have a single non-zero eigenvalue, which is 1. And there is no information, useful information there. You just get something trivial. You don't see the edge from the integrated spectrum. So the proper way to cut your system is not to cut it into the orbital space if you want to see something for the new equal 1. You have to do something a bit more fancier. You have to redo the cut in real space. So you have to take your space, divide it in two regions, A and B, and do the calculation of the reduced density matrix. So what I will describe now is actually not specific to the integer quantum mole effect. Each time you want to do a real space partition of a system, this is the calculation that you have to perform. Actually, let me just erase this. We don't need it. So take any orbital. And look at the creation operator C dagger, where you create one particle in this orbital, right? Say phi r. Let's call C dagger acting on the vacuum, r equal to phi r. I can split this creation operator into two. I can write it as, so this creates one electron in the orbital phi. I can cut it in a creation operator that creates a particle that only lives in A, and a creation operator that will add one particle that only lives in B. So alpha and beta are constant. C dagger A creates an electron living only in A, and the same story for C dagger B. So of course these are creation operators, so they should satisfy the proper algebra, so you still get that C dagger the anticommutator of C dagger, C and C dagger should be equal to the anticommutator of CA and C dagger, CB is equal to 1. So, of course, and all the other anticommutators are equal to 0, right? So if you use this relation here, you will find that alpha, the norm of alpha square plus the norm of beta square has to be equal to 1. I can now compute the alpha and beta just by this formula here. So my orbital, I can always split it as theta A of r, phi r, plus 1 minus theta A of r, phi r. So it's like the Heaviside function where it's equal to 1 if r belongs to A, and 0 if r does not belong to A or belongs to B. Right now it's something trivial. I just say that I can write my wave function on something that has a non-zero value only on A, and something that only non-zero value on B. So let's call this guy here up to some normalization factor by a new function phi A, and this one phi B, right? I want these wave functions. So this is going to be the wave function associated to the creation operator CA dagger, and this one will be the wave function associated to the CB dagger. They have to be normalized. So I want, if I integrate over R, I want this to be equal to 1. So from there you can obtain what are the coefficient alpha and beta are just this NA and NB, which is just the normalization factor. So NA is just the integral, the square root of the integral only on A, dr of my initial, of my orbital phi r. This one is on B, dr phi r square. And you check that NA square plus NB square is equal to 1. Right? Your orbital, the wave function is normalized, so when you sum up, when you take the square and you sum up, you get just the norm of phi r, which give you 1. And all of that, you get that alpha is NA and beta is NB. Okay, so now we have, for each orbital I can do this work, this job, to split it into two wave functions. One wave function that only lives in A and another one that only lives in B. So tracing out of B on B will be to remove all the B parts of my creation operator. Do you have any questions? So far, so good? Okay, so I think the rest is going to be like 20 minutes, so I would prefer to make a break right now, and so I can give you the full derivation of the integral spectrum for the integer quantum Hall effect just after the break. So let's come back in 10 or 10 minutes. So I've shown you how to perform the real space partition for a single orbital. That's nice, but not really useful. You don't get much more information out of that. So we want to do the same kind of partition for the integer quantum Hall effect, for the nu equal 1 state. So the first thing we should wonder is how to cut the system into two. Remember, we use the symmetric gauge. So you have the droplet, you have some rotation symmetry. So of course, in principle, we can cut the system in any way, right? We can decide to do like a T shape or like a cat or whatever the shape you want to give. But it would be great to preserve this rotation symmetry. Like for example, if you have to perform these integrals analytically, it will be much easier if you have the rotation symmetry. So let's do that. Let's cut the system. So let's take a circle of radius r, capital R. This is going to be the part A, and the outer ring will be the part B. So two advantages for this kind of cut. The first one is this integral. So now I can do this job that I've done here for any orbital, Cm, da-da-dum. Just have to add indices. And actually now I know exactly what the alpha and beta are. So they are the N, M, A, N, M, B, and this is exactly what I have here. If your cut preserve the rotation symmetry, then the thing is that we will be able to use the angular momentum as a good quantum number to label all the levels within the entanglement spectrum. So that's another reason. It's not only because these integrals are simpler if you use this cut, it's also because you can use a quantum number to classify your levels. So let's, I can also put a square here. Just this one is 1 over 2 to the power m factorial integral from 0 to r dr r to the power 2m plus 1 exponential minus r square over 2, and this one is 1 over 2 to the m factorial integral from r to infinity of dr r to the power m plus 1 minus r square 2. So if you want, you can plug these integrals in your computer and get the number for a given r. So first, all the states, the phi A, M, you still have the orthogonality, right? if you have m is still the angular momentum, so if you take two different m values, the two states are orthogonal. And same story for the phi p. So the simplest non-trivial example beyond one particle that you can look at for the integer quantum Hall effect is the integer quantum Hall effect for two particles. If you write it in first quantized and second quantized notation, you just apply to the vacuum the operator to create one particle in the orbital 0 and one particle in the orbital 1. Right? It's just the nu equal 1 state written in second quantized notation, where I occupy all the orbitals from 0 to the number of particles minus 1, which is in that precise case just the orbital 0 and 1. Good. And now I can basically plug this expression here into this formula. Let's go. So this one will give you n 0a c dagger 0a plus n 0b c dagger 0b and 1a c dagger a 1a plus n 1 b c dagger 1b acting on the vacuum. I can just expand this formula here. So I will write down three terms. I will get n 0 a n 1 a c dagger 0 a c dagger 1 a acting on the vacuum, plus another term which looks very similar, which is n 0 b n 1 b c dagger 0 a c dagger 0 b c dagger 1 b acting on the vacuum, and a final term which is n 0 a n 1 b c dagger 0 a c dagger 1 b minus, just using the fact that the c dagger anti-commute, n 1a and 0b c dagger 1a c dagger 0b acting on the vacuum. Good. So here you immediately see that up to some normalization factor, it doesn't matter. But this three terms, you can understand them physically. The first one means that you have two particles sitting in A. The second term is two particles sitting in B. And the third one, well, you have two states, but in both cases, you have one particle in A and one particle in B. You can check by summing up all these coefficients here, you get one. So which exactly you need for the trace of the, just by taking the square, and you will get that the trace of the density matrix is 1. So that's the, and it's already like in the Schmidt decomposed way. These states are orthogonal. You have this is the state for A, for B, for A, for B. The state for B here is trivial, it's just a vacuum. The state for A is trivial, it's a vacuum. So it's the Schmidt decomposition of the two particle nu equal 1 state that you and when you cut your system in real space like this. The nice thing with the integer quantum Hall effect is you can actually do the calculation for any number of particles, and you can write down the formula for this. So the nu equal 1. So when you do the Schmidt decomposition of the nu equal 1 state, you will have states where you have 0 particle in A, 1 particle, 2 particle, up to the maximum number of particles in your system, n. So this is what this sum means. You have a sum over all the angular momenta of your system for the part A, and then a sum over all the configuration. So LZA1, LZA-NA, such that the sum of the individual 1 to NA is equal to LZA. Then you have a product of N, that's for the LZA I going from 1 to NA. Product over I equal to 1 and B. Here's the coefficient A. Get LZB I for B and the configuration LZA I LZ B I. So just to give you the notation here, LZAI is just the many-body state for NA particles where I fix the total angular momentum of my system. This is up to a sign, but this sign doesn't matter for when it comes to the counting or to get the Entanglement spectrum. It's just the many-body basis for the part A. And you can do the same thing for the part B. So that's the LZ, BI. That's the many-body basis for B. So just to give some flavor, if you think about boxes, remember that you start from the original nu equal 1 state. Well, this is the LZ, 0, 1, 2, 3, 4, 5, 6, 7, let's see, 7 boxes. Oh, let's make 8. So you completely fill all the boxes from 0 to 8. You have 9 particles. So when you do this decomposition here, you find all the possible way to pick NA particles out of these 9 boxes. So one possibility, if you take, for example, NA equal to 4, we'll have I can pick this, so I will get LZ1 equal to 0, LZ2 equal to 4, LZ3 equal to 5, and LZ4 equal to 7. Of course, once I made a choice for NA, the number of particles in A, and all the LZA of these NA particles, the part B is completely fixed, right? So the part B will be just all the remaining particles. So I have 1 here, 1 here, 1 here, 0, 0, 1 here, 0, and 1. So NB is equal to 5, and I can look at LZB. 1 is 1, LZB2 is 2, LZB3 is 6, LZB 1, 2, 3 is, sorry, this is 3, this is 6, and LZB5 is 8. So once again, it's just a way to divide into two groups of Na and Nb particles this set of 9 particles, right? And for example, if you wonder about the sign, well, the sign is just when you take the tensor product of this state here and this state here, you have to reshuffle all your C-dagger operator to sort them from 0 to 8. This is how you will get the sign correctly. Okay? It's exactly like this exercise here, where I decide to put the A part on the left and the B part on the right, whatever happened. So that's why I have this minus sign here. The minus sign is just when you recombine these two guys to get this one, there is a minus sign. So let's look at the case where we cut. Imagine that you have an even number of particles and you look at a given sector of Na. So you don't look at all the Nas, you look just at one value, let's say n/2. So, quick question: what is the configuration that gives me the minimal angular momentum for this Na particle? How should I build this state with the minimal angular momentum LZA? Any idea on that? Right. So you have your N boxes. You have Na particles. The boxes are the label from 0 to n-1, and the angular momentum is just the sum of the occupied orbitals times the angular momentum of the individual orbital. So if you want to create the state, the medibody state within this basis here with a minimal angular momentum, the easiest way to do that is to just say we need one more. 5. Uh, 0, 1, 2, 3, 4. Is there? Yep, there is one more. 11, 12. Should get an even number. 10 and 12. Right? There is a single state with a minimal LZ. It's the state where you put all your particles to the left. Right? And the momentum of this guy here, you have to sum 5 plus 4 plus 3 plus 1 plus 2, which is 15. Okay, so that's the state with a minimal LZ value. Now the next LZ that you can look at has to be bigger than 15. So the next one is 16. And you can check that this is the only way to write a state with 6 particles and getting the momentum LZA equal to 16. You just have to promote this particle to the next box. So if you remember the construction of the many-body spectrum for the edge mode, it smells like exactly the same thing is. You can look at the next case, LZA equal to 17. Then you have 2 options. You can either promote this guy here to the next box, or promote this guy here from here to there. So it's 0, 1, 1, 0, 0, 0, 0. That's LZA equal to 17. And so on. So if you look at the entanglement spectrum, this is the Schmidt decomposition of your state. So we can extract the weight out of that. So if I look at a specific block, a specific region of the entanglement spectrum, I will focus on Na equal to n over 2. Na is a good quantum number when you do the cut, right? I mean, you can explicitly check that. If you use in second quantized notation, the operator that measures the number of particles is really the sum of the number of the operator that measures the number of particles in A plus the operator that measures the number of particles in B. So that's why Na is a good quantum number when you do the entanglement spectrum. And of course, the other guy is the angular momentum of your system, the total angular momentum. Same story, it's the sum of the angular momentum of particle living in A and the sum of the angular momentum of the particle living in B. So this is why these two guys are good, the L, Na and the LZA are good quantum numbers when you look at the entanglement spectrum. So if you look at the entanglement spectrum, for this example, you will get one state at LZA equals 15, sorry. One state at LZA equal to 16. Another state, actually 2 states at LZ equal 17, right? These are the 2 states that you obtain. I don't give you the numerical value for these guys, but the spectrum, if you do the calculation with your laptop, this is what you would observe for the system. The next step, you will get 3 levels, and the next one will be 5 levels. So, if you only focus on the counting of how many states you observe in your entanglement spectrum, when you look at this number of particles, the number of states that you get per momentum sector is identical to the number of states that you have per momentum sector for the edge modes of the new equal 1 state. for the chiral U1 boson. So just, at least in terms of counting, you get the proper result, the one that you expect. So that's the entanglement spectrum of the integer quantum Hall effect looks like the H mode of the integer quantum Hall effect. It goes beyond just simple counting. If you look at the values themselves, well, you will see linear slopes like you expect for a chiral H mode. So the eigenvalues, well, the entanglement energies, xi, will be proportional to the momentum. So that actually, if you want to be more rigorous, the statement that I make is the following. In a finite size system, what you observe is get the proper counting per momentum sector. So that's exactly what you expect for the H mode. The same counting that you expect for the H mode. It follow roughly a linear behavior. There are two deviations to the H mode of the integer quantum Hall effect in finite size. In finite size, you don't get the exact degeneracy. Remember when I've built the many-body spectrum for the H mode, all the states in a given momentum sector, they all have exactly the same energy. If you do the entanglement spectrum for the integer quantum Hall effect, you have some small splitting of the degenerate state. If you increase the system size, if you take more and more particles and look, for example, all the time at a given perimeter and a given number of particles, this splitting will go to zero in the thermodynamical limit. So that's a first deviation to the edge mode dispersion relation. The second difference is in finite size, you see that at some point you won't get the counting of you will have deviation to the counting of the edge mode. Well, the reason is quite simple. Look in this example. There is a minimal value of LZA. Right? I put all the electrons to the left. The maximal value of LZA that I can create is to take all these electrons here and move them to the rightmost part of the boxes. So if I fill all the boxes here from 6 to 11, this is the maximum LZA value that I can create. And there's a single state. Now, if you look at this value of the angular momentum for the edge mode, there is a given number of states, which is clearly bigger than 1. For the edge mode, the degeneracy always increases with the angular momentum. So these are the two deviations, but they are only finite size effect. Right? If you increase the system size, this will disappear. So this is like a very nice example where you start from the ground state. Once again, you start from the nu equal 1 ground state. You do this calculation of the Schmidt decomposition or the entanglement spectrum. And what you observe, what you extract from the ground state is the edge mode physics. So you get access to the edge physics just by looking at the bulk wave function and doing this calculation. Maybe one thing here, you might wonder, wait. Why looking at single NA value? What's going on for the other values of NA? Well, for each value of NA, you will get exactly the same spectrum. I think that I've never pronounced the name, but so the entanglement spectrum was introduced by Lee and Haldane in 2008. I think the guiding spirit, I mean, looking at the eigenvalues of the region symmetric was not really new. I mean, if you think about DM energy, people were using that in their code for a long time. I think the key point was to say, okay, I want to, by fixing the proper quantum number and plotting the eigenvalues in the right way as a function of some other quantum numbers, I should get access to the edge physics. So here, by fixing NA to n over 2, it's like looking at a small droplet of the integer quantum Hall effect. Okay, but I have some freedom now. If I just look at the new equal 1 state, everything is frozen. But if I remove some particle, then I have some freedom. So that's why I will get access to the edge mode. So it's important here that we only focus on one sector of NA, because we have this picture that when we cut the system, we should first get like a smaller droplet of the new equal 1. And then just by increasing a little bit the LZ, we'll get information, we'll see the edge mode developing. So actually, we can be a bit more quantitative about the statement that this is the edge physics. Right now, I've only talked about the levels themselves, the counting, and to some extent, to the eigenvalues themselves. I had never talked about the eigenstate. By eigenstate of the reduced density matrix, I mean that if you look at the Schmidt decomposition, remember the psi I over 2 AI bi. These are the eigenstates of rho A. So right now, I have to say that these guys mimic the energy spectrum of the edge mode. But what about these guys? Well, you have one example of the AI. This is one of the states. So you have to be careful. The spectrum itself will mimic the edge mode. Now, if you look at the eigenstate of the reduced density matrix or the AI of the Schmidt decomposition, these states, these wave functions, are actually the full-fledged wave function. You've got the bulk part, and here you've got the bulk plus the edge. It's like, remember the Zi minus Zj, this is the Zi minus G, product of the Zi minus Zj. This one is the product of Zi minus Zj times the sum over all the Zi. It's a bit more tricky because the basis that you use here is not the phi m basis, not the full orbitals, but the phi ma, where you truncate, where the wave functions only have a non-zero value in the A part. So it's just the wave function, the wave function of the integer quantum Hall effect, the new equal 1, but written in a very strange basis. But still the physics is there. It's the wave function of the bulk plus the edge. Any question? Yep. The gradient. The slope? That's a really good question. So it's not, you don't extract the velocity of the edge mode, right? This is not a universal property. Of course, you can extract the velocity here, but you cannot relate it to the velocity of the edge mode of the true system, right? So that's, thank you for the question. It's actually a very good one. Any other question? Okay, if not, the last thing I would like to talk about this morning, I will still stick with the non-interacting case, but I would like to move on to the simplest example of a topological insulator that you can consider beyond this example, which is also a topological insulator, of course, but some kind of lattice model that will help you if you want to look at a time reversal symmetric case. We'll talk about channel insulators. So last week you had an introduction to the channel insulators, the Haldane model, so you know how to compute the churn number out of it. So that's exactly what I will do now. The reason why I want to look at this example here is because you may claim that the integer quantum Hall effect is actually a very specific model. And actually there is one criticism that you can make. If you look carefully, I've told you that, for example, the IKRT model, we have this amazing reduction of the number of levels in the anti-quantum spectrum. We go from something exponential, increasing the system size to only 2. Here, actually, the number of states that you observe is saturate the Hilbert space dimension for a given NA and LZA. So there is something a bit specific about the integer quantum manifold from that perspective. So let's look at a more generic system, I mean less a specific system with where you can also extract the same kind of properties. You have many shared intuitor models that you can build like, and of course last week Karian talked about the Haldane model. It's called the two orbital models. It's quite kind of simple to write down. You can write a simple type binding model that will give you exactly this block form for the Hamiltonian. You can drive the system from a trivial phase to a topological phase just by changing the chemical potential, this M, the chemical potential on the system. So if M, the modulus of M is lower than 2, you get a non-trivial band with C equal plus or minus 1. And if you have M bigger than 2, you get a trivial insulator. You can put your system on a cylinder, right? So this is the lattice model that will give you this Hamiltonian, this time band. And you put it on a cylinder, and you look at the dispersion, the band structure, and you can still use kx, the momentum along the cylinder, as a good quantum number. And depending if you set M to be within the topological regime or the trivial regime, you will get two different spectrum. This is a trivial regime. It's an insulator. There is a big gap here, and these are the two bands, the valence band and the conduction band. And now, if you set M within this region between -2 and 2, well, if you have an open system, you will get all the Bragg regions, which is basically the state in the bulk. And the blue curve is the edge mode on one end of your cylinder, and the red mode here is actually the edge mode on the left side of your cylinder, right? The chiralities of these two modes are opposites, right? One goes in one direction, the other one in the other direction. So this is all you can see, but I think, Karian, you show some picture of the Haldane model like this one for. So this is roughly the same calculation. So we can do exactly the same calculation that we have done here. Once again, if you can easily write down the wave function if you completely fill. So let me just go to the next slide. Yep. Good. So let's take the system in the topological phase. Let's put the Fermi level within the gap. So we completely fill the valence band here. So we can write down the wave function for the system, where you have the Fermi level to here. It means that's just a Slater determinant of all the occupied orbitals. It's exactly the same calculation as this one. We can split each orbital. Remember, you write it here as a C, K, X, whatever. So you can split into something belonging to A and belonging to B. So which means that if you take your cylinder, you cut your cylinder into two, you will get the part A, which is the left part, and the part B is the right part. If you do the calculation for this guy, you will get exactly the spectrum here. It's exactly the same thing going on. You will get the same counting. Actually, it's quite interesting because it's a many-body spectrum. So remember at the beginning of this lecture, I've shown you how to go from the one-body spectrum of the edge mode to the many-body spectrum. And you can wonder if you can somehow go the other way around, meaning like this is a many-body spectrum, many-body entanglement spectrum. Can you extract a one-body spectrum out of that? And actually, this is some calculation that you can perform. So this is what we want to achieve at the very end here. What we would like to do is the following. We have the reduced and density matrix for a system. So I can write it like this. Xi, I, A, I, A, I. And I would like to say, well, up to the exponential, I should get the Hamiltonian of the edge of my system. So this one is the entanglement Hamiltonian. Okay? So the claim is this guy here up to some constant factor, because, well, I can always rescale the energy as I want. I should get, it should mimic the same kind of Hamiltonian that I have for the edge mode. The nice thing with this story business of chain insulator, actually for topological insulator, I think it was the calculation was done by Fidowski the first time. Once again, at some point you will get notes about everything, so you will have all the references. There is something quite specific about this, the non-interacting system. Since you start with a single Slater determinant, you can actually prove that this Hamiltonian here can be written as a one-body Hamiltonian. So you can write it like this, H of Kx, I, J, so A, I, and J are sites or orbitals, if you prefer, in more generic sense, in A. And I can still use Kx as a good quantum number, right? Of course, here I break the translation symmetry along the y-axis, so that's why I still have to use the index for the orbitals. But I can do the Fourier transform along the x direction and use Kx as a good quantum number. So the Hamiltonian will be diagonal in Kx. So this is really this possibility to write down the Hamiltonian as a one-body Hamiltonian is actually really specific to the fact that your wave function, the initial wave function, can be written down as a single Slater determinant. Otherwise, it's not always possible to write down this as a one-body Hamiltonian or even as a two-body Hamiltonian when you have an interacting system. So without going into the very details of the calculation, this h of kx, which should have two more indices I and j, you can extract it from the propagator. So if you note the propagator only in A, j of kx, which is just there is this simple relation that G, the transpose of the propagator, is 1/1 plus exponential of h of kx. So once you compute this propagator, you can get access to h of kx. So h of kx is the one-body Hamiltonian, that one-body entanglement Hamiltonian of your system. And if you look directly at the eigenvalues of G of the propagator, you will get two different behaviors depending if your system is in a trivial phase or topological phase. So the eigenvalue of GA, if you're in trivial phase, they will accumulate either at 0 or around 1. So that's in the trivial phase. So it sounds like looks like the valence band and the conduction band of your chain insulator. Now, if you drive the system to the non-trivial phase, so if you look at let's say the valence band, and you compute the eigenvalues of a propagator GA, you will get a bunch of eigenvalues close to 0, a bunch of values close to 1, but then you have eigenvalues that will go continuously from 0 to 1. And actually, these eigenvalues are like the edge mode of your system. What you see here, remember that when you fix the Fermi level, it's like freezing the edge here. So the edge here doesn't play any role. Like in the Arcetri model, we remember we were looking at one ground state by fixing the SZ. So there was nothing. There was no contribution from the two spin 1/2 at the end, only from the degree of freedom that you have at the edge that you have. I mean that you had the edge that you have created by cutting the system into two. So it's exactly the same story here. You fix the Fermi level, so completely freeze what's going on at the edge here, and what you observe within the eigenvalues of GA is really like the edge mode. Once again, you can also look at the wave function. I mean, somehow here is just a nice way to reconstruct, to extract the one-body spectrum out of this many-body spectrum using the propagator. But still, if you just the main idea here is really that whatever the system you look at, this topological phase, if you do the entanglement spectrum calculation, even if it's a non-interacting system, you extract the physics of the edge by looking at the bulk function. So tomorrow what we will discuss is what's going on when we have a 2D topological phase, an interacting phase. And I will focus mostly on the Laughlin state. Well, I think you already know the answer. You will get exactly the same kind of result. Namely that if you take the bulk Laughlin state, you will get at the very end access to the edge mode. And actually, you can do even more than that. If you cut your system in a different way, you can access the bulk excitation of the system only from the ground state wave function. Okay, any questions? Apart from getting some coffee and nope. Okay, so then let's stop here and start tomorrow looking at the interacting case. Thank you.